Welcome to the DC-MUSE University Industry Webinar Series. My name is Stephanie Lee. I am a professor in the chemistry department at NYU and affiliated faculty with the chemical and biomolecular engineering department. And today I will be the moderator of this session. This webinar is part of the DC-MUSE series to bring together academic and industry stakeholders that happens about once a month. And today we will have two talks, 15 minutes each, one by Professor André Taylor, and then followed by Dr. Walker, who is the founder and CEO of Badwater Alchemy Holdings. So first I'll introduce Dr. Taylor. I'm sorry, after the research presentations, and we'll have 25 minutes for Q&A. So first I will introduce Professor André Taylor, who is a professor in the Chemical and Biomolecular Engineering Department at NYU. He leads the lab Transformative Materials and Devices, and he is also the center director of DC-MUSE. His research focuses on a broad range of applications from fuel cells, batteries, and solar cells. But today he'll be presenting his work on redox flow desalination. So André, the floor is yours. Thanks.
All right. Thank you so much for the introduction, Stephanie, and very excited to have everyone here. Let me pull up my slides real quick. Thank you so much, guys, and very excited to talk about our latest technology. So it's a redox flow desalination system. And Stephanie mentioned, my name is André Taylor from the Department of Chemical Biomolecular Engineering, New York University, and this is our DC-MUSE webinar series number 4. And I'm the acting director for DC-MUSE. And this project is a very exciting project. And I'll talk a little bit on how we're using advanced ion separation to bring this about. First, I wanted to give you a little bit of background on on desalination and some of the work. So really, the background is freshwater crisis, and there's a need, right? And if you look at global water, over the long run, there's been a steady increase in the demand for global water. So of course, as population is increasing, there needs to be more techniques in terms of how to, mitigate this global water crisis. And when you look at a variety of different sources for water, then of course there's the seawater, which is 97% of the available water. Brackish water is 0.9. So really the fresh water that's available is only 2.5%, right? And a majority of that water is locked up in the glaciers, which are rapidly melting. And there's some in our Great Lakes, but a majority of this is not very accessible to majority of the people. So when we take a look at, let's see, is this, so the demand for fresh water is actually increasing. And then in particular, AI, there's also a strong need for AI for fresh water as well. And that's become a very big issue. And in fact, when I was in Louisiana a couple weeks ago, in the most rural part where my family's from, and near Delhi and Lake Providence, not too far from Monroe, Louisiana, Meta's building a $10.5 billion system there, AI system. And those systems are going to need their own power system. They're going to need their own AI. And it's amazing because driving from one end to the other is about 5 miles long for that. So really, water is going to be a big issue, is going to become even more of a bigger issue. So when we talk about desalination, so we need to make it more cost effective, right? So we're talking about 100 million cubic meters of fresh water daily that needs to come through. And 26% of the water sector uses energy for this consumption, and it generates about 120 megatons of CO2 annually. So there has to be some sort of effective way for scaling to pull this forward. So the general scheme of seawater desalination, start with feed water, you go through a pre-treatment step, and then you have a saltwater tank, and then you have some sort of technology for desalination where you can actually separate the water from the contaminants, and then followed by post-treatment. Now, majority of the techniques that are used, of course, we use non-renewable fuels to generate this. But then there's the opportunity for new renewable energy. So if we can take that from the grid to use that to power the source. Now, in particular, the minimum amount of energy to desalinate soluble seawater is 1 kilowatt per cubic meter of electricity. But desalination incurs 50% of the economic cost for water. So we look at the global desalination capacity and the different technologies that are used for this. Majority of the technology is desalination, followed by multi-stage flash. And in particular, when you think about multi-stage flash, this is just high technology of evaporation, right? So solar, or actually just using using hydrocarbons to burn or actually boil the water to where you can actually evaporate it. And surprisingly, of course, in regions like, for example, when I travel to to Abu Dhabi and different places in the UAE, they're using a lot of thermal multi-stage distillation, because you have readily available um, you know um, gasoline and thermochemical process, things like that. But the challenge is that what's actually happening to the balance when you're generating CO2, right? So there's a high fossil fuels cost, it's very inefficient, and you have a 70% brine waste that you have to deal with and get rid of. Now, the heavily studied or the state-of-the-art technology that's used for this is the reverse osmosis. And reverse osmosis, requires putting a heavy pressure on a membrane, and then you're actually pushing the water through and hopefully rejecting the water ions to go through that. But again, you have 50% brine waste with that, low carbon emission, and cost effective for seawater. But there's some challenges with this. Now, if you look at electrodialysis is a series where you're taking different anion-cation exchange membranes, and you're actually separating this by applying a bias to the system. So if you have a cation exchange membrane, you can allow your positive protons to go across. Your anion exchange membranes, your negative anions can go across through the membrane. It's ideal for brackish water, recovers more water from seawater, and it can be used for a wide variety of applications. But the drawbacks of this is it's too expensive, right? So it takes maybe 100 cell pairs for practical distillation, which is about 75 times more expensive than reverse osmosis systems. So we developed this system in our group with this redox flow battery system, and this is using commercially available redox mediators. In this case, we're using sodium ferrocyanide or ferric citrate. In this case, what happens is you have the cation exchange membrane, anion and cation exchange membrane in this configuration. You have feed water that flows through the bottom, goes across. And what happens is you have this redox mediator. So you have this redox mediator, which is oxidized on the anode side, travels across, it migrates, it combines with the ion, which goes through this proton exchange membrane, creating, in this case, sodium. You circulate it around, and it picks up an electron, and then, once you circulate it around, then you end up with a concentrated stream. So on this side right here, you have your anion exchange membrane where your chloride goes through. So you have a concentrated brine stream, and on the right side, you have a freshwater stream. So you can imagine, if you have this system, if it's very, very long, then of course, this concentration of seawater can go all the way down to drinkability. This concentration goes up higher, higher. Or if you think about it in terms of, if I recirculate this, right? So if I have a fixed volume, if I recirculate this over and over again, run this through, and using renewable energy to power the system, then you can think in terms of like an amount of time for a fixed volume of water that you can desalinate. This redox mediator can be recycled back through and used again and again. Now, there are some challenges with that, but I think this is a very promising technology to move forward in this area. And so Akwe, who's now a postdoc in the group, he developed this system during his PhD thesis, which is the investigation of flow rate symmetric flow channel redox flow battery desalination system. And he actually designed the system using CAD, and built the system using our makerspace, where he actually shows how the system can be very, very viable for seawater desalination. So he did a very, very detailed study in terms of how to increase the flow rates for redox performance at high voltages, how increasing the flow rate reduces resistance at the electrolyte membrane. And then he showed in particular how the flow rate disparity across the channels increases over potential and electrolyte crossover. Now that's important because when you think about this in terms of a system, if you're taking renewable energy, which is nice, you have to have some sort of technique on how to optimize the flow rates. What are the ideal flow rates? What are the ideal conditions to put this together? Now, as I mentioned earlier, if you compare redox flow batteries to electrodialysis, you can see here that the energy consumption is very, very high. For electrodialysis, you have to have a lot of cell pairs to be comparable to the amount of energy required for a redox flow battery system. And I think that's the advantage for this. You have to have like maybe 30 cell pairs to achieve comparable redox flow battery performance. In particular with this, if you compare reverse osmosis with electrodialysis with the redox flow desalination system, you can see some of the metrics right here, right? The energy consumption is very, very low. The CO2 production is very, very low for the system. And in particular, the cost for water. If you compare this to electrodialysis or reverse osmosis, you can see it's very, very comparable in terms of cost per water. But the nice thing about this is your feed water fouling scaling tolerance is very, very high for redox flow battery systems compared to reverse osmosis. So there's some potential in that. And your water recovery for the redox flow battery system is much higher than state-of-the-art reverse osmosis, which can be greater than 91%. Now, these numbers are taken from our work that we've done in our group, and then also some of the work that's done in the literature. So I'm going to show you two examples right here of our systems and then pass it on to our next speaker. We have a first generation redox flow battery system where we have a 1 liter salt solution reservoir. We have in situ model with a stirrer where we can actually monitor the system, and then it's an RFD cell. So we built this from the ground up, and I'll preface that with Aquay built this from the ground up in terms of putting this together. And you can see the RFD cell from the first generation, and then from the second generation, you can see he's made some improvements and how the flow puts together. And it talks about, he has some descriptions on the zero gap tolerance that he put in and the flow rates and optimizing those parts. In particular for these system, here's an example of the zero gap right here that I'm talking about in terms of putting this in. But when you put the system together in an exploded view, you can see all of the different components right here for the system to put together. You have your nylon mesh, your anion exchange membrane, cation exchange membrane, putting this all together into one complete system. Okay, so let's see. So comparing these systems together from the first generation to the second generation, and this is a little bit of a complicated graph, but I'll walk you through it. ASSR, that's your average salt removal rate. That's the amount that we want to see how much salt we're removing per area per time. If you look on the right scale right here, this is your charge efficiency, which shows like how efficient this is from the charge that you're putting in. And then this E reactor, which is this red line right here, which is your energy for the reactor that you're consuming. Now, at a given flow rate, and this is at the same applied voltage. So if I'm applying a voltage of 0.8 volts at a given flow rate right here, let's say, for example, at 5, for this first generation, I get about 200 ASSR. If you look at the second generation of the same conditions at 5, you can see I can get almost an order of magnitude higher ASSR. So there's a lot of areas for improvement, which is exciting for this that we can put in and move forward on this. So I'm very excited to see what more we can do, and I think there's some opportunities. This is where I wanted to engage with the community because there's opportunities in terms of the materials, the membranes, the flow rates, the cell design, also in terms of the redox mediator itself and putting that in. So with that, I will conclude with some work that we're doing with the X Prize, and we made it to the next round for the X Prize, which is funded by the Mohammed bin Zayed Water Initiative. And so I'm very excited about that. This was us actually just a few weeks ago during the Climate Week here in New York. And so we've advanced. And so the whole idea is to build these systems, make them commercially available, and keep advancing through the system. With that, I was able to meet Badwater Alchemy, who's also working in the competition as well. And that concludes my part of the talk.
Great, thank you so much, Andre. So we will hold questions for the Q&A session after Dr. Walker's talk. So as you think of questions, feel free to put them in the chat and then we'll get to them then. So our next speaker is Dr. Bill Walker from Badwater Alchemy Holdings. He has a background in geochemistry and for the past, I think 35 years or so has been working on water treatment and just recently started his own company. He's the founder and CTO of Badwater Alchemy, which is looking to commercialize desalination systems using nanometals. So Dr. Walker, please, the floor is yours. Sorry, you're muted. Let me see if I share.
Oh, yeah. Yeah, there we go. Yeah, that's actually good.
Okay,
Yep.
great. So just let me know when you're ready for me to advance each slide.
Yeah, thanks. I'll just dive into it. I'm really, folks listening and watching, I apologize for that. So try to get through this and let you know what we're up to. But yeah, we're also, as Andre mentioned, we're also working on desalination. We're doing it a little bit differently, more of a conventional, if you will, in the terms of adding chemicals to a solution and looking for removal of salt in that manner. Next slide, please. And what I want to kind of go through today is just some quick background on how we got to this point, what our desalination process looks like, and then a little bit on the nanoparticle media itself and what we think is going on in terms of salt uptake. We've also been running these reactors now for about 3 years, so we have quite a bit of data. So I just wanted to show some examples of some of our high salt removal rates, a little bit of a discussion at the end on our solids, which a lot of the people that have approached us about our technology have always been worried about solids and what we plan to do with those. So a lot of emphasis in our company right now is focused on solids, but as well as projected cost estimates, which are if you have investment money, you all know that that's all they care about is cost estimates. So anyway, we won't say any more about that. So next slide, please. So just quickly, I discovered this process in 2010. As Stephanie mentioned earlier, my background is in geochemistry. My PhD was in geochemistry. My other degrees are in chem, but I spent a good 40 years in the mining industry building water treatment systems, typically at what's called legacy sites. And these are mining sites worldwide that have been closed. And when they're closed, they just flip the switch on the pumps and they walk away from any beneficiation that they're doing on site and leave all the equipment. And what happens, of course, when they flip the switch on the pumps is all that water that they used that they were pumping out of the mines to keep it dry while they were being worked flows back in. And all of a sudden, within about 5 or 10 years, depending on ambient groundwater flow, you're usually faced with some kind of a pretty nasty, depending on the ore deposit itself, you're going to be seeing typically an acidic flow of water coming out of the mines. And my job in a good part of my career was looking at ways of using media to have the water flow through, and as it flowed through media, different contaminants would be removed. Typically, we are always looking to adjust pH, remove metals, and at some point, somewhere around 2008, the regulatory agencies got very interested in osmotic pressure. A lot of these effluents started to empty into streams, and a lot of biologic life was wiped out because of it. And so they started to impose what they called osmotic pressure, which we know more commonly as TDS. And so TDS is real challenging. It was like, well, how do we get salt out of water? That's not going to be easy, especially the way we were approaching it, which is we don't have any infrastructure to work with. We have no electricity at all. So how do we possibly get salt out of water? And that's what got me thinking about, how can we do this in a really sort of a simple approach to salt removal? And that led to the discovery in 2010, where I had been working with nanoparticles and a lot of different nanomaterials, copper particles, zinc, iron primarily, looking at different size fractions, surface areas, and all sorts of different things, and trying to find anything that might work for salt removal. And I did find that I could get, depending on the initial salt level, we could get as much as 30% of the salt out. And as soon as I saw that, I realized, you might have something here. This is pretty impressive to see that much salt coming up. So I spent the next 9 years self-funding this operation, and just tried to get a better, really worked on two things. One was to improve the rate of the reaction, to get it go a lot faster. Initially, it would take about 2 to 3 weeks, sometimes 2 to 3 months for salt to be removed, and which in itself is not bad for an example in an agricultural application. It's actually fine. In the West, where they use impounded water and have a lot of salt in that water, you could add nanoparticles, and over 6 months, it could desalinate pretty well. So an application like that is maybe down the road. But at any rate, I was really interested in trying to find something that could move faster and obviously get to more than 30% removal. I've been kind of had 80% in my head as a kind of a number to shoot for in terms of removing salt. When I talk about salt, I'm really talking about sodium and chloride as well. That does include other cations and anions that are removed by the process, but it's all primarily sodium and chloride. Anyway, got a patent in 2019. 2021, we established Badwater Alchemy. Since then, we've grown to about 10 people, about an even split between scientists and engineers, and some administrative, and our CEO. At this time, I'm glad Andre brought this up in the beginning, but right now, our focus has been on produced water. Some of our funding has come from oil and gas, because they're facing this situation in West Texas and eastern New Mexico, where they have no water for agriculture. They have really run out. But they're producing 1 million barrels, which is 42 million gallons of produced water every day. And after they treat produced water, it has a little bit of BTEX in it, but it's mostly 96% sodium chloride. And the rest of it are just sulfate, calcium, magnesium, and a few other cations and anions of much lower concentration. So our focus in the last 2 years has been on treating produced water, and we're planning on putting our first pilot in the field in Q1 of 2026. The seawater application is something we've been very interested in from the start, but given the reverse osmosis kind of dominance in the thing in that area, we haven't done too much of it, except we do realize that one of the applications of our technology could be to do the heavy lifting on salt removal, because our system works really well at high salt. And we can take out most of the salt in 20 or 25 minutes and leave the seawater maybe from starting at about 40,000 milligrams per liter of sodium and chloride at about 9 or 10,000, which would put it in a pretty nice spot for really high efficiency reverse osmosis. There, from what we've looked at in the literature, their efficiency would increase from about 40 to 50% up to over 85% if that initial salt came down to that level. And this is the space that we're kind of working on right now for the X Prize, is working with seawater. For me personally, what I am trying to do, though, I've always thought that the best use of our technology was in agriculture. That's primarily because the chemicals that are used in this can be obtained almost any place worldwide. In fact, they're very common in many farming areas. Some of these chemicals are just easy to get hold of. And I see this as a really interesting application for irrigation and saline aquifer restoration, where we could pump water from the subsurface that's saline, maybe at 30 or 40 millisiemens, treat it, and then re-inject it, and continue to do that until the aquifer is restored to something that could be used by local farmers. I think it would be potentially a game changer for many parts of the world that simply don't have any water for agriculture. So we'll see how we get there, but right now it's sort of on the back burner. We've approached some of the farms in Southern California, Arizona, about their interest in possibly piloting it. And so we have some discussions going on, but nothing quite to the same extent as, for example, the X Prize, which is well-funded and a lot of competition. So with that background, I'll just kind of give you an idea of what our system looks like and how we think it works. Next slide, please. Sorry about this slide. I'm not going to be able to see much, but I have some photos in here, so it'll be a little bit easier as we go forward, but let me just describe it verbally. It's a very simple system. We really, if you can just imagine a bunch of reactors in a series. We've used anything from 12 to 24-inch PVC at about 5 feet tall. Presently, we're using 55-gallon drums. And what we do is we make a nanomedia, and I'll get into that in a minute, but the nanomedia is a very dilute slurry, and the slurry is introduced along with some zinc oxide into our, what we call a reactor train. Each train consists of 3 reactors, and we feed each of those reactors the same amount of the nanomedia. And after the 3rd reactor in the first train, the solids are building up that are formed from the removal of salt. So we run that water into another vessel, and in that vessel we have potassium hydroxide to raise the pH up to about 8 to 8.3. And then we add a flocculant, and right now we're using a polyacrylamide, which is pretty common in the industry. And that bulks up all of these solids and they fall out. Most of our solids will fall out in about 15 to 20 seconds after we add the PAM, the polyacrylamide. And the clean water then is advanced to the next train, where there's another 3 reactors, and we repeat the process down the line until we get to the water quality that we are looking for. At this time, we're using about 9 reactors or 3 trains to bring the salt level of produced water down from about 130,000 milligrams per liter down to 25,000 milligrams per liter in 3 trains. Seawater, we expect to probably be able to do it in 2 trains. But I'm going to hold off a little bit on that discussion because there's a bit of interesting technology that we need to complete our system. So continuing with what we do, the solids themselves have to be separated and dealt with. So what we do is we take the solids that have been separated, as I described, with the potassium hydroxide and the PAM. We put those through a conical, what do you call it? Cone bottom tank, and it has a solenoid at the bottom. We open the solenoid when the tank fills, and we drop it into a dewatering bag. And the dewatering bag is just a passive means of removing mostly gravitational water that's in the solids. And we collect that and store it. And then the water that drains from the bag is run back in, because it's a higher salt content. It's run back into the front of the system and it gets treated again. And we just keep repeating this process until we achieve like I said, the water quality that we're trying to get to. Now, the interesting thing about the system is that, like I said, we're very, very, very good at high salt. But when we get down to about 15 to 20,000 milligrams per liter, our system requires a lot of media to get any more salt removal from that. So we're looking for a conventional technology or a new technology to complete our system. In the industry, we call it polishing. It would be our polishing unit at the end to get us to a water quality that would give us either a drinking water type quality or something that could be used for agriculture. And the nice thing about our system is we're not really adding anything except iron and a little bit of sulfate and a touch of zinc here and there. So there's not a lot in there that we're adding that contributes to any potential problems with regulatory agencies. And I really shouldn't say that because I probably have just jinxed this process. The providing proof, I think, on nanoparticles introduced into the environment might be something that's going to be a real struggle. I know that other researchers have noted in the literature that they've had to do a lot of work to convince regulatory agencies that they are safe to introduce into the environment. So we're going to have to visit that when the time's appropriate. So that's the basics of our system. It's very simple. We use, like I said, we use different trains with different size reactors depending on different waters that we treat. But this is pretty much what we've been going with for the last 2 years. And it's the same system that we're going to do for the X Prize as we gear up for that starting next week. Next slide, please. Oh, we can skip this one. I just went over this. That was another terrible slide. Sorry about that. So this is what it looks like in the shop right now. This is what we're constructing. Really the same view, 55-gallon tanks. If you look at the first, let's see, I'm sure you can't see my cursor, but if you look at the picture on the left, this is a run that I started with last week. It was really just, you know, we call it smoke and leak testing just to make sure the electrical is all good and there's no leaks at the valves, et cetera. But we have a water tank that you can't see, a 3,000-gallon seawater tank that we made with its synthetic seawater. Making 3,000 gallons was interesting. And we pipe it overhead to that first blue tank on the right. That's where the water goes in. At the same time, the 3 pumps on the stands to the left of the first tank are the dosing pumps. They're just simple peristaltic pumps that deliver a small amount of the nanomedia. And the nanomedia is in the carboys sitting on the floor right in front of the pumps, that black fluid. And so we dose them all the same. We have done a lot of work on dosing to get to this point, but we have a lot more to do because we're pretty sure we don't need to dose as much as we have used in the first train as we do in the second. So we've got work to do on that, but it's a real simple system. So that's what a train looks like. And then the middle picture is just kind of looking down the line. You can see the second train and the third train in the blue barrels beyond. And that conical tank that's elevated, that's where the separation process is going to work, where you pump the solids up there. We're awaiting the dewatering bags and the container that it comes in, and that'll sit right below that. And between the two, there'll be a solenoid valve on that conical tank to deliver the solids in there. And then the picture on the right is just another view of that. Next slide, please. So here's for us, we've been working on this. I've been particularly working on this for a long time, trying to figure out exactly what's going on in this media and why it's removing so much salt. As I note here, we've removed sodium and chloride, but we also take out metals, magnesium, calcium, and potassium. We take out about 50% of anything that shows up in there. We manufacture it. This was an interesting process going through. I did a lot of different stuff with taking larger nanoparticles and grinding them in a shatter box to get them down to nanomaterial size. Started a lot of fires in those things. It's, those nanoparticles can be burst into flame pretty easily. The way I ended up doing it was using and part of this just goes back to the cost of chemicals, using sodium borohydride to reduce iron to the metallic state is extremely expensive. So we just did what a lot of folks are doing, and that's going into the green methodology of looking at plant extracts and using natural polyphenols and catechol to do the reducing step for us, and that's what we're going with right now, and it works really well. The interesting thing, and I don't think I brought it out in the slides, is that we get pretty good removal if we use just iron nanoparticles, or they're doped a little bit with copper and zinc, but we don't get the same removal as we do when we add the organics from, we're using tea that we get from black tea. When we combine the two, we get almost 80% reduction versus about 30% with both of those components alone. And we have some ideas on what that means, but it's really interesting to note. But as far as what's going on, this is pretty well established that when you have these nanoparticles made from either purchased or made like we do with reduction with polyphenols, when you introduce it into salt water, chloride catalyzes the reaction of iron corrosion. And it starts a sequence of events that they refer to typically as green rust. And green rust is known to pick up chloride. And so we think that clearly it's some of what we're getting in our reactors is due to the green rust reactions. The reaction that so far we've noted is typically finished in about 25 to 35 minutes. It's pseudo first order with respect to sodium chloride concentration. We keep the pH from 3.9 to 7, and doesn't seem to matter too much where it goes in that range. But if we go above 7, then things don't work very well at all. And it works differently, but not to the same extent. We keep the ORP, oxidation reduction potential, is between minus 500 millivolts and plus 500 millivolts. And it's all done under pretty much anoxic conditions. We keep dissolved oxygen down below 0.1 milligram per liter. And we have had waters with higher oxygen coming in, but once we've added our media, we seem to pretty much scavenge all the oxygen out of it. So it seems to work just fine. Next slide, please. So here's one of the interesting things too, and people ask us all about this a lot. We're reporting that we remove as much as 50 grams of sodium chloride with less than a gram of zero valent iron added. And this is, pretty remarkable. I've always treated this, at least experimentally, as an adsorption reaction, where we're just looking at the adsorption of salt as with an iron rust that is growing and polymerizing, and the surface area and the surface charge are increasing over time. And that's why it's taking up so much salt. I'm not so sure anymore. And I think that the energetics, as far as where's the energy come from this reaction, I'm pretty sure it's associated with the corrosion of iron. There is a lot of energy released from that. Some of that was just noted in Andre's talk this morning. And we think that there is some battery similarities between what we're seeing and doing in our reactors, sort of inadvertently, which is driving our reaction to remove as much salt as it does. But there's also another possibility for this too. The corrosion reactions typically will result in oxyhydroxides being formed. Some of these iron oxyhydroxides are tethered to the surface of the original nanoparticle, but some of them are also independent in solution and tend to form. And we're trying to figure out what conditions, what are called layered double hydroxides. And layered double hydroxides are what we call in geochemistry a brucite structure. And it's a structure wherein you have these sheets of alumina and silica, but in between is this interlayer space, and the interlayer space is really good at trapping things like chloride. There's another mineral called oxygenaite, which when it forms has sort of a tunnel-like appearance, and it's also capable of trapping chloride. And then the charge imbalance created by chloride adsorption is satisfied by the adsorption of a counterion on the surface of the mineral. So these are what we're looking at as probable species that are removing salt. But I just want to show one more thing that we're just getting into. Next slide, please. And just quickly, these are stability diagrams, just pretty common geochemical approaches to looking at where your water quality might be able to tell you what mineral species could be forming. And if you look at the one on the right, there's that GR chloride, that's green rust chloride, and that's exactly where our water chemistry goes. We're right in there about pH 7, 8 at the highest, and up to about 0 on the EH scale. So we fit kind of right in there. Not exactly all the time, but it's generally in the region where those things are known to occur. Sort of indirect evidence of what we're talking about here. Next slide, please. This is the interlayer space I was talking about, a brucite structure. This is the side view. So here's one of the sheets on the top, the lower, and that interlayer space, the darker circle in there is chloride, and that's how it gets trapped in there along with hydroxide ions, et cetera. So depending on what the solution is composed of, you can get, a number of different anions adsorbed in this inner layer space. And let's see, next slide. And we can skip this one.
Bill, I didn't want to I appreciate the talk, but we wanted to give a few minutes for the discussion as well.
Yep.
So
Yep.
so if you don't mind, if we can like wrap up, because we only have like 9 minutes. So we wanted to
I
try to give some.
can do that. Absolutely. I was watching here and I apologize for that. I got off track a little bit. Yep, this is the last, I think this is what I was talking about. This is a metal organic framework with the polyphenols. And we have observed these. I have a colleague working on this metal hydroxides at high pH, and he's observed these fluid-filled pores within his metal hydroxides. And this is the kind of thing that I think is probably happening in our reactors, which explains some of the really high salt content, where the fluid-filled pores rest inside. They're about 1 to 5 nanometers in size. And this framework can basically trap the sodium chloride within its structure. Anyway, next slide, please. Okay, quickly, some data from our produced water, just showing here. We start with an initial chloride, for example, of 86,000. After it's gone through 3 trains in our reactor, it's down to 20,000. Sodium decreases from 38,000 to 11,000, an average of 73% reduction in the reactors. Next slide, please. This is another produced water from eastern New Mexico. And this one is a similar, starting a little bit higher, 76,000 on chloride, down to 18,000 for 77% reduction. And next slide, please. Our reactors, produced water stored. Next slide, please. Sorry about that. And this is it. This is the last slide. Our solids from the system, about 9 to 11% of the total water volume that's treated. Going back to what's going on with the salt removal, we do know that when we collect the solids, that we can wash off 70% of the salt that was removed simply by washing it with water, and we can recover the rest by washing it with a dilute acetic acid, for example. That brings up, can we recycle these things? So we're going to look into recycling of our media. Estimated capex for this system is really inexpensive, about 170,000 to 220,000. Our present estimate of cost of treated water is about 1/10 of a penny per liter. That's pretty much in the range of what an RO can do. And our consumables, aside from the tea, are actually really easy to get. So hopefully in the future, we'll be able to get a good source of tea and figure out how we can do it even more cheaply. Thank you very much. I am finished.
Thank you so much, Dr. Walker. All right, so we are going to open the floor for questions. Let me see. I think. Okay, go ahead, Taeyang. You can unmute yourself.
Okay, thank you so much. I have a question for Andrea. Just so you know, I'm Taeyang. I'm located also in New York State, but upstate New York. Just so you know, I'm glad that we are in the same state and working on the same topic. I have a question for your, you said you have competition for X Prize. Can you tell us a little bit more about that, especially regarding the challenge that you have to overcome maybe for the next several years, especially regarding seawater desalination, which is known to be not as effective in terms of using electrochemical separations versus membrane separation? Thank you.
Yeah, sure thing. Yeah, thanks for the question, and glad to see you on board. And yeah, I'd love to follow up and talk with you a little bit more. Yeah, so the X Prize, this is the largest prize for water, and I guess they've given that, as you may know, there's been several X Prize competitions. You know, everything from solar to other applications. And this X Prize, the charge is to build a bigger and bigger system. So we made it through the first round, the qualifying round, and there was prize money that was involved with that. The next round is to build a system that can do 1 cubic meter of water. That's the track A. So there's 2 tracks. One is to do 1 cubic meter, so it's about 264 gallons in a day with a 80% uptime, and taking that water all the way from seawater concentration to to drinkability. And then there's a couple other nodes on there. I can send you the timeline on that, but eventually they want to do 1,000 cubic meters per day, and that's the end all be all prize. And that last prize, there's a $250,000 step for this next win for the qualification, goes up to a few million, and then I think the last prize is about 5 million on there. But yeah, and this is it's a big prize competition to build up for scale up.
Thank you.
Thanks.
Track B, there's also track B, which is also component tracks that you have to integrate into systems and things like that. So there's 2 different tracks for that. Yep.
Hi, how's it going?
I think.
I can't.
Oh, Edward, do you want to say something?
Yeah, how's it going? Sorry, I couldn't figure out how to do the raise hand button, but I was listening in on your call, and I noticed that you guys were talking about how there was sort of a bottleneck in terms of your in terms of being able to source NABH4 for the system. Is that correct?
Are you asking me or?
No. So sorry. All right, so I'll just phrase it as a statement then. I noticed that the process requires NABH4. I just wanted to let you know that you know, like our company's technology, it's bonded through the Department of Energy, and so NABH4 is a natural byproduct of our blue hydrogen production process. So if at any point you know, you guys are looking to scale up and, you know, like build a larger process, which may entail, you know, a larger stream of NABH4 just for the reagents to scale up. You know, like, and if you ever need a partner, in terms of that supply chain, you know, we'd be happy to sort of create a new stream.
That's awesome. Thank you so much.
Yeah, no problem.
That
And I
is
think Edward
wonderful.
shared the contact info in the chat.
Yeah. Yeah. So NABH4 is our way to help the Department of Energy meet their $1 per kg of hydrogen goals. You know, everyone's talking about like pink hydrogen, blue hydrogen, geologic hydrogen. We're the last piece to fit that. We do solid hydrogen. So, you know, down the road, I think this would be a great, you know, new fit.
Thank you. That's wonderful.
Yeah.
Partha?
Yes. My question is for Bill Walker. And so I'm from ExxonMobil. And I'm curious about your water desalination. Are you able to also remove significant quantities of lithium in your experiments, or does the lithium chloride stay in water?
Good question. Yes, we've started looking at lithium a few months ago. We have 2 produced waters that you may know about that we've been working on over the last 2 years. One of which is very low in lithium, less than 2 milligrams per liter. I think the other one is higher at maybe, I have data within my reach, but I better not do it. I've had a hard time getting things up today. Let's say it's probably up around 100 milligrams per liter. The last lab assay that we received on the lithium suggested that we could only remove about 20% into our solids, suggesting that most of it stays in the water. So that could be useful because it could be trapped upstream or downstream of our reactors, but it's not partitioning into the solids like we thought it would, because I'm not sure our solids are going to be necessarily easy to extract anything from. The whole idea of harvesting other metals from the solids and even upstream of it before it goes into the reactors is something that we've just started really looking into, but it's a great question. I wish I could give you more, but right now I can tell you that we're not removing very much in the solids.
Okay, thank you.
Sure, thank you.
Great, thanks so much. I think we're coming right up on 12 p.m. So I think we will conclude our webinar. Andre, did you want to say any closing remarks?
So thank you everyone for taking time out of your busy schedule to be available. Special thanks to you, Stephanie, for moderating, and for Bill for you coming on board and taking time to be a part of this. And this series is part of 4. This is number 4. So we have 3 more if you want to look on YouTube. If you look on our website, dc-muse.org, and you can see our previous webinars that we have. And our contact information will be on there. This is recorded, and we're looking forward to more discussion. So hopefully this will kickstart more discussions. Also, if you have any interest in topics that overlap with our interest for DC-MUSE, so Center for Decarbonizing Chemical Manufacturing Using Sustainable Electrification, please reach out to us. In particular, our program manager, Simon Mashallah, who you probably have all received emails from. You can write to him, and he can relay that to us. And we thank you for your time. Thank you so much.
Thank you.